1, 0. We have commit and we have liftoff at 2:13. The Saturn V building up to 7.6 million pounds of thrust, and it has cleared the tower.
The Pass the Torch series is open to the public, and it is a great way to reconnect with our history and learn more about specialized topics. And again, we're pleased this year to feature the Year of Apollo and the Pass the Torch series, both here at the Space and Rocket Center and also at the Huntsville Public Library, where we have another 2 events next week, one at each location. So we want to say thank you to our panel members for participating and contributing. We want to say thank you to our supporters and those who have come, and to those who are helping us here at the Rocket Center this year. Intuitive Research is our Apollo 50th Golden Anniversary sponsor. And if you haven't, please take the opportunity to visit the Intuitive Planetarium, which is now open here at the Space and Rocket Center as well. Logicor has stepped up to be our Pass the Torch event sponsor. They're a growing company with a highly qualified workforce, and we say thank you very much to Logicor for supporting this year's Pass the Torch. A couple of other entities that we would know. Glen Raven Incorporated is a fabric-based, market-driven solutions company, and they have been providing for support for digital archives, and we thank them very, very much. And we want to thank our planning committee chairmen, particular on this particular initiative that we had this year. Heidi Collier of the German American Heritage Committee, and Benny Jacks and Jack Stokes of the NASA Contractor Legacy Committees of the Apollo Community Planning Committee. We quickly learned those 2 committees really came together to work on these series of panels. It has been very enlightening. They've done a fantastic job. We want to thank WHNT-TV for stepping up and being one of our media partners and helping us recording these oral histories. And we also want to thank Rocket City Digital Media, who is also recording panels. And I know the TV station is working on podcasts, and I think Rocket City Digital Media is also working on podcasts. 10, 20, 50 years from now, we want to be able to archive those who have provided commentary and insight into the challenges of Apollo. So we thank all of those people as well. And on behalf of Dr. Deborah Barnhart and all of us here at the Space and Rocket Center, Rebecca Hitt and Kay Taylor, April Adcock, and all of the folks, Heather Roden, I think, who have worked in the education section, have really worked hard behind the scenes to put these programs together. Our panel today is the engineers of the Apollo era, moderated by Mickey Allen, and I think Mickey is going to come up and maybe give a brief background on him and the panel members, and we'll turn it over to them in just a minute. 3 weeks ago was the flip side of that, the contractors of the Apollo era. Today are the engineers on the NASA side of the Apollo era. And without further ado, thank you all for coming. And Mickey, please come up and introduce your panelists today. I can do that.
Thank you. About a year ago, I was invited out here for a meeting. I had no idea why I was invited, but I came out anyway. Turned out Deborah Barnhart was trying to pull together this 50-year celebration. There was a lot of panel discussions they wanted to have, and I volunteered to pull together 2 of them. One of them was on the contractors that worked during the Apollo period, and the other, the Marshall engineers that worked during the Apollo period. What you're going to see here today is a representative of some of the engineers. At one time, Marshall had nearly 7,000 people, just people working for NASA. So these guys are trying to kind of give you a taste of what some of us went through. And I will say this, we couldn't have been out there at a better time. We had more fun. We all looked forward to coming to work, and we worked a lot of hours. Some of us got paid overtime, some of us didn't, But we didn't care. We just had a lot of fun doing what we were doing and knowing we were going to the moon. That was the big thing. We had an objective, so we went. And you're going to hear about a little bit of that today. First off, let's get the next chart. We're going to be speaking from over here on the side because we need to be pointing back up here, and trying to turn around and do this is kind of tough. So I'm going to walk back over here. Anyway, the panel members. The first one that's going to talk about, well, I'm going to give a little introduction, so leading into these guys. But Ron Bledsoe, Ron, stand up for a second. Let them know who you are. Hey, Ron, stand up. And believe me, we were not asleep when we worked back in the 60s. Clyde Nevins, the structures. When I took this job of trying to pull the panel together, I just thought I was going to have everybody else speaking, but it turns out you stop and think. This is the 50th anniversary of the landing, and we started this nonsense over 60 years ago. I was not able to find somebody in the fabrication area that felt comfortable about giving the presentation. So I pulled together some charts that I found, and I'll show them to you, and you can do that. Next, though, is Mr. Test himself, Ron Tipu. And I'm not going to ask Brooks to stand up. He has, that's okay. Well, you going to get up? No. All right, this is Brooks Moore. He's Mr. Instrument Unit himself. Okay, next chart, please. The other way. Next one. Believe me, we had problems with this the other day when we did a dry run. Okay. I'm going to talk to you a little bit about the Saturn V vehicle itself. And then I think it's kind of important that you know some of the key milestones and decisions that were made prior to the commitment to go to the moon. And then after the commitment, there were some key points that I thought I'd bring out. And then I'll show you what the Saturn V launch vehicle did in terms of missions and so forth, and then summarize it. So Jack, if you can give me the next chart. This is the Apollo 11, the first moon landing launch of the Saturn V. And you look at the Saturn V vehicle and you say, well, I think anyway, it's beautiful. And it is. It looks simple, but let me tell you, that is one complex vehicle there. I want to pull some of my notes here because I don't want to forget them. Number one, the first stage is 33 foot in diameter. To kind of give you a feel for that, I measured a while ago, back there at the back, all the way across in the chairs is 33 foot. So all of you are sitting inside of the diameter of the Saturn V, first stages. It's 365 feet tall, which is taller than the Statue of Liberty. The takeoff weight was 6.5 million pounds. And somebody came up and said, well, that's more than 25 fully loaded jets. Now, I don't know what jet airplanes they're talking about, but I know one of them is that Boeing 737 is not one of them, since it's not flying. And the F1 engines burned up 534,000 gallons of fuel in 2.5 minutes. That is 3,567 gallons a second. So you can see it was thirsty. Somebody sat down and said, oh, how many parts do we have? I think it must have been a co-op that they put to do that. But anyway, they came up with 3 million parts, roughly. And I believe it, by the way. It's a lot of it. There's 70 miles of electrical wiring. You think about it, that's 3/4 of the way to Birmingham. And by the way, my wife and I go to the Broadway Theater Leagues, and one of the first things they tell us, please turn off your cell phones, because it is kind of distracting when you're trying to talk. Now, I'm not trying to embarrass you, by the way, but there are 91 engines on that beast up there. 16 of them provide forward thrust. The rest of them are attitude control things. Every one of them has to work perfectly. You think about that. If you look at the first stage here, it's got to separate here from the S2 stage, and this part here also has to separate from the S2 stage. So as soon as the S1c shuts down, you think about it, and they're getting ready to separate. Well, they got to activate the separation mechanism between the two. But all the parts are going at the same speed. So what you've got on here, you've got 8 little solid rocket motors to slow down the S1c stage so that the S2 will go away from it. Okay, now, what's happened to the propellant in the S2 stage? As you can imagine, as soon as you shut down, the propellant's going to start sloshing around. So now you've got to settle the propellants back down before you start the S2 stage. There are 8 what we call Ulrich motors, solid rockets, to speed up the S2 stage a little bit, settle propellants, and then you start the J2 engine. That happens here and up here also, the same kind of situation. So it's complicated. There were 6 major contractors at Marshall: North American, Boeing, Douglas Aircraft, 2 Rocketdyne contracts, and IBM. These contractors had 283 major subcontractors. And these contractors, those 283, had contracts in 27 states. Then in addition to those 283, there were 100 other smaller contractors that were not considered majors. And these 283 gave the parts and everything. The peak manpower during the Apollo program was 420,000 people operating in 20,000 companies. Now that 420 includes industry, NASA, and academia. There's another little thing about this thing, though. Right up here at the top, that's where the crew sits. When you have crew, you have to man rate the vehicle. And that adds another whole complication to the whole thing. And I'm talking about man rating from here down to here. You have to have anything that could fail safe, or if you have something that has to have a redundancy like the instrument unit, you've got to have some redundancy, sometimes triple redundancy. I'll tell you a story about later on in my career. I was involved with the payload of flying on the space shuttle. We had to have some little bolts, not very big. Contracted with a company out in California, and they had certain specifications that they had to meet in terms of how strong they were and so on and so forth. Plus, after so many building of the bolt, they had to pull one from just random, pull it out and test it and certify that it was in fact like it's supposed to be, met the specifications and requirements. For some reason, this company decided that they didn't need to do that. They got caught. The owner of the company was found guilty. He was fined and sentenced to prison. So we took it very, very seriously about having a man rating. Okay, next chart, please. The first line up there, you're all aware that the Russia beat us, putting us first satellite. And I might mention that Dr. von Braun and company, who at that time worked for the Army and the ABMA, had said, hey, we could put up a satellite earlier. And he was told to cool it, that the Navy had been selected to use the Vanguard to put up the first satellite. So Russia beat us. And in hindsight, frankly, I'm kind of glad they did. In the early 50s, or not early, in the 50s, we were doing a lot of different studies about going to the moon, going to low Earth orbit, going lunar, going solar, whatever. And it became obvious at that time they needed a bigger engine of 1.5 million pounds of thrust. So in early 59, the contract was signed with Rocketdyne to build the F1 engine. The specific impulse of it, this is RP1 and LOX fuel, was 263 seconds. We needed an engine that was more efficient, if you will, and a guy named Abe Silverstein had a committee pulled together to look at using liquid hydrogen and liquid oxygen, which had a 433-second specific impulse. Dr. von Braun was one of the 7 members of this committee, and at first he was not wanting to use liquid hydrogen because of the volatility of it and how cold it is at a minus 433 degrees Fahrenheit. But he did agree that if we were going to go to the moon, we needed it. So they signed the contract then with Rocketdyne to build that J2 engine with 200,000 pounds of thrust. As a result of these, and this kind of surprised me because I'd forgotten this, that in January of 1960, NASA told Congress that yes, we can go translunar by the end of the decade and land sooner thereafter. President Eisenhower gave NASA the highest national rating that you could have in terms of going to the moon. Then the thing that got everything really going was the fact that Russia put up the first man. And if you notice the date here, it's the 12th. The day later, President Kennedy called a meeting at the White House and he said, what do we have to do to beat the Russians? Because at this time frame, we were behind them they were beating us big time. So he signed Vice President Johnson to see what could happen. Johnson, I understand, sent out 9 letters saying, what can we do to beat them? Dr. von Braun was one that came back and said, hey, we can land man on the moon returning by the end of 1967. I think his bosses kind of said, let's add a little contingency on top of that. So the next chart, I think most of you are aware of this. President Kennedy said, by the end of the decade, we can put man on the moon and bring it back safely. So that turned us on. Next chart. Really turned us on. If you notice well, first off, we've been launching down at the Cape, some vehicles, but it didn't have the facilities or anything to handle a Saturn V launch vehicle. So they got 150 acres, square miles of land to build the facilities to carry it. By the end of the year, we had all 3 contractors on. Douglas had already been on board, but they were directed to modify the S4 to use 1J2. North American, they were told, we don't have our specifications and requirements really set and solid yet, so be prepared for some changes. And sure enough, some did come down. Let me get it here. Okay. NASA approved the Saturn V configuration, even though even prior to that we were still working it. Again, we were looking at 2 different ways going to the moon, Earth orbit rendezvous and lunar orbit rendezvous, Dr. Von Braun agreed with the center director at JSC that in January that it would be lunar orbit rendezvous, and then we instrument shot. There were two major decisions made. In my opinion, I'm amazed that they were made. One of them was the one you see here, all up testing on future Saturn V flights. That means the first stage, second stage, third stage, the instrument unit was operational, the service module was operational, and the command module was operational, but could be done without men. Dr. George Miller met at one of the meetings and said, hey, we've got to do this if we're going to get this done before the end of the decade. Some of the people here at Marshall thought he'd lost his ever-crazy mind. This had never been done before. Marshall had said that it's going to take 10 unmanned launches, 6 manned launches, and finally landed on the moon on the 17th one. So you can see there was a big discrepancy between what they're doing here and what we thought we needed to do. But the decision was made. We're going to go all up. And as soon as that decision was made, everybody fell in line and made sure that we could do it and do it successfully. Next chart, please. Okay, here's what happened. 11:57, we had all-up launch, unmanned, and it was completely successful. We all kind of stuck our chest out and said, aren't we great? And it was great. The second launch, though, there were 3 anomalies. It did not, the mission was successful, mainly. Okay. The 3 anomalies were that we had a pogo problem on the first stage, which could have been catastrophic. We had 2 engines go out on the second stage, but the others burned longer, so we still got to where we wanted to go. Third stage, the J2 engine did not reignite like it's supposed to. So needless to say, we had several meetings to got that resolved. But here's the other big decision. And that was to send men around the moon on the 3rd Saturn V launch. And the first time you put men on it. And one of the reasons they wanted to run on the moon, they wanted to beat the Russians. And the LEM was not available at this time frame to be tested. So I don't know how many of you may have been alive at the time when they circled the moon on Christmas Eve and they read passages from the Bible, but it was very moving and very emotional. If you didn't cry, you didn't have a heart. This was the low Earth orbit flight to test these 3 together. This one, they were in lunar orbit, and they were to go down within 9 miles of the lunar surface and then come back. I understand that Stafford was told, now, if you go on and land on the moon, you do not have enough propellant to get back up into orbit, so you better just not try to land. I don't know whether that's true or not, but I wouldn't be at all surprised. Okay, on the 6th Saturn V launch, they landed men on the moon and brought them back safely. Now, folks, that had never been accomplished before, and it hadn't even come close to it since. But anyway, then we ended up through Apollo 17. I might mention that the payload capability at this time frame was like going towards towards the moon was 80,000 pounds. On Apollo 17 is 116,000 pounds. Okay, I've taken long enough. Well, wait a minute. I'm sorry. This is the key thing right here. There were 48 launches in here. Not one failure. Some of the statistical people said they thought if we had 50% success, we'd be lucky. So we feel like we did a if you'll pardon my French, a damn good job doing what we did. And these guys did it. I didn't, but they did. Okay, with that, Ron Bledsoe, would you take over?
Don't forget to give your resume. He forgot. It's on.
Okay, can everybody hear me? Anyway, I'm going to stand back here, and I'm Ron Bledsoe. Actually, I'm a native Huntsvillian. I graduated from Huntsville High School here in Huntsville, and went to Vanderbilt on a scholarship, and went into the Navy as a naval officer, went into flight school, and ended up with the 7th Fleet before I left the Navy in 1957 and started working for Aerojet General Corporation, which was one of the 3 contractors back in the 60s and 50s that we had. That was Aerojet General Corporation, Pratt & Whitney, and Rocketdyne. Also, I had worked for Rudy Beichel. Rudy Beichel at Aerojet General Corporation was one of the scientists and the engineers that actually came with von Braun in 1950, and never actually worked for NASA, but he turned around and went to and worked for Aerojet General Corporation. I worked on the Aerojet engines back in that day. Those engines actually that I worked on, the first and second stages, were of the Titan vehicle, contracted by Martin Company. And so also the J2 engine contract, which was part of the second and third stage of the Apollo vehicle. I worked on that engine, and interesting enough, our work ethics under the Germans and everybody else and the Americans were very tight. One night at 12 o'clock when we left home, I got home at 12 o'clock, and Rudy said, "What are you doing going home so early?" He said, "We've still got work to do," and I expect, so I turned around and headed back to work, and I worked till 3 in that morning, and then got up the next day and started work at 7 o'clock. So those are the kind of work ethics that we were used to in the engine program. I came and worked, then I was went with NASA in 1960, and let's see. Hey, Jack, move that first. Yeah, there you go. In 1960, became the F1 project engineer in our laboratory. And so I worked on H1, F1, J2 engines back in that day, but primarily I worked on the F1 engine. On the F1 engine, until the Apollo began to slow down in the 70s, and then I moved to the shuttle main engine and worked on the shuttle main engine. In that office, the chief engineer's office, and then was after Challenger blew, then some of us went to another major organization, which is the Mission and Safety, and headed up with Alex McCool, which I'll show you in just a moment, and ended up one of the directors for that group before I retired. Okay, next chart. This right here is Sonny Mariah. This is what we looked at. Most of these guys, all of these guys are mechanical engineers, and also not only the mechanical engineer, they're all rocket propulsion engineers. And interesting enough, Sonny Mariah was actually come from New York. He graduated from New York City College in 1954, and then he went into the Army as an officer, was detailed back to Redstone back in 1954 and with von Braun team. Worked under General Medeiros, and in that position, they moved, all of these guys moved to NASA in 1960, 61, and 62. Alex McCool, so anyway, Sonny became also not on the F1 program, but later on he became the Lunar Rover program manager. Alex McCool is the youngest guy in this group at 95 and still moving like a machine. And that's what NASA does, is train those people to live old. And so the rest of us are in our 80s. Richard, anyway, Mac was head of that new organization after Challenger and ended up being the shuttle program manager. Richard Brown graduated from the University of Tennessee and worked in the program office supporting Sonny Mariah. And he has also been a Sloan Fellowship for Stanford University out in California, and been a manager the rest of his time with NASA. This guy here graduated from Iowa State University. He came from the old farm in Iowa, got his master's in mechanical engineering at the University of Alabama, became a turbopump expert, worked on every engine in solving turbopump problems that we had on the F1, H1, J2, SSME, and throughout his career, he was worked with all the people all over the country in turbo machinery. Dave Arnett, he worked on the components, the gas generator, and the heat exchanger for the F1 engine back in that day. Then he became the chief engineer for the lunar vehicle. And that you don't recognize that guy, but anyway, this is Lynn Twirlin. He graduated from Auburn. He was one of the Auburn graduates in mechanical engineering, got his master's also from Auburn, became one of an outstanding propulsion engineers that solved many of the problems that we had, as Mickey alluded to, with von Braun. Bob Richmond, he graduated from Ohio University as a mechanical engineer, and we had a combustion and stability problem on the F1, H1. He spent several years, which I say several years, 2 or 3 years, in solving that problem and working with people all over the country in getting that worked on the F1 engine. Jan is our youngest guy up there in his early 80s. He was a test engineer and went on to be a manager and one of the managers, and now he also is a consultant from SLS. Next chart. That's just another chart. That's the F1 engine. All these engines, by the way, you can see here at the Basin Rocket Center. Next chart. What? That picture was taken in March of this year. Those taken, all those guys were taken. This is taken back in the Skylab. That's Karl Heinberg, who headed up the test lab. Oh, I'm sorry. You had another question? Anyway, Herman Widener was the deputy at our laboratory. These are in Dr. von Braun, and they were working Skylab problems here with Jack Stokes, which is the guy that's flipping the charts. Okay, next chart there, Jack. Rudy Beichel is the guy I work for at Airjet General Corporation. Next chart. Rudy Beichel, Karl Heinberg was the head of Test Lab. Went over to take over the propulsion vehicle engineering laboratory, in which I was fortunate enough to work for him on the lab level with for all the engines, F1, H1, and J2 engines back in that day. Next chart. This is Dr. Marazzi. He was the head of that laboratory and was our boss in that respect. Next chart. Hans Paul was our head of propulsion division back in that day, and a real gentleman and an outstanding leader, and we all worked for Hans Paul back in that day. All the Germans, as you know, have passed away. Okay, thanks. And anyway, next chart, Ted. Herman Widener was Dr. Marazzi's deputy, and we called him Mr. Propulsion. Next chart. J.R. Thompson. Everybody recognize J.R.? J.R. actually graduated from Georgia Tech and came to Marshall from Pratt & Whitney in 1963 and joined the engine group and was one of our engine guys. He was a workaholic. We called them workaholics. A lot of the engineers were workaholics back in that day. J.R. actually continued on becoming the Marshall director, then became the deputy administrator, and then came back to Huntsville and headed up the orbital science company here at Marshall before he passed away. Next chart. These are what we looked like back in the 60s and 70s. Keith Chandler was a technology man. Werner Voss was in avionics. Jack Halbrooks was down at Stennis, where we tested engines there. Carlisle Smith was an engine systems guy. Larry Ware was in the program office. Joe Lombardo ended up being the propulsion division chief, and then went on to be the head of the solid rocket motor out in Utah. Jerry Thompson was a guy that I worked for, and all of these guys worked for him except Larry, and he worked in the program office, and that was me when I was a couple of years younger. And this is Dick Rogers. He was the project engineer for the J2 engine. And anyway, as far as history is concerned, go to the next one, chart, Jack. This is just a shot of the V2 engine, which actually I put it up here to illustrate the engines that were similar. Was the Jupiter engine and the Redstone engine. This is the first stage of the Titan vehicle, which we had propogo problems with the Titan vehicle. It helped also solve the problems we had on Apollo. Next chart. Oh, I'm sorry. Yeah, pogo is oscillations in the tank, in which they took and was one of the significant problems that we had during Apollo, but it was in the stage area, not in the engine area. But that was the oscillations that we had in the tank area as far as sloshing is concerned. You know, when you load propellants in that tank, that was the problem we had was what we call pogo, and that was the oscillations. This right here is the H1 engine, which was on the Saturn 1 vehicle. The RL-10 engine was the upper stage for the Saturn 1 vehicle. This is the F1 engine. This is the J2, which is on the second stage. Next chart. These are just a comparison of the RL-10, H1, J2, F1 engine as far as thrust levels are concerned. Next chart. This is just a comparison of the vehicles in which we put in the various engines. The Redstone engines, Jupiter, C, Mercury, and Jupiter there. Next chart. On the H1 engine, this just gives you the characteristics that on the Saturn 1, we had 8 of those in the first stage. This is the vehicle that they actually flew on, and this is the thrust level of those. And next chart. This is a Saturn Rockets of the all successful launches, and this just gives you a comparison of the Skylab and the Apollo launches on Saturn 501, and this is the Skylab launches. And those are the dates in which you can get a feel for when we launched those. Next chart. The F1 engine, which was the largest engine that we have ever in the world, and no one has ever built, Russia or no one, has built anything stronger and better than that engine. She was a tremendous workhorse that got us as part of the first stage of the Apollo vehicle. Next chart. This right here is in manufacturing at Rocketdyne. This is Dave Ulrich here. He was a program manager of the F1 at that time. Next chart. This is still another chart of the F1 engines in manufacturing. Next chart. These are some of the features of the Saturn V, the F1 engine. You can see it was the largest engine ever built, and the pumps could remove water out of an Olympic pool in a few seconds. We burnt more fuel in 1 second than Lindbergh used across the Atlantic Ocean. Significantly, that rocket went on from paper to design in 6 years, which is a tremendous feat. This right here, if you go down to the Cape, that's the VAB building that we call the VAB, but it's a vehicle engineering building, and it was designed for the Saturn V vehicle, and is now used for the shuttle system as well as the space transportation system. And anyway, next chart. This was a J2 engine, and this is the vehicles it went on. It was 5 of those engines for 1 million pounds of thrust. A little over 1 million pounds of thrust was the second stage of the Apollo vehicle, and was the first, and also in the third stage of that Apollo vehicle. Next chart. Saturn, this is Saturn 11. What's interesting about this vehicle here is the fact that we lifted off with the weight of that vehicle is over 6 million pounds of thrust. 6 million pounds, I said talk about thrust. 6 million pounds as far as weight is concerned. That first stage actually lifted off with 7.5 million pounds of thrust and moved that entire vehicle up to 46 miles above the Earth. And also, then the S2 stage, which had 5 J2 engines on it, over 1 million pounds of thrust, lifted us up from 46 miles to 116 miles above the Earth. The third stage, by the way, those stages, as you probably know, are all in the ocean. I mean, they expended. The third stage was sitting, waiting, and after we reignited that one engine there, it actually took, for 2 more minutes, expended, it actually got us into Earth orbit around the, and then that third stage, then it shut down and restarted and went for another 5 minutes toward the moon. And it was carrying payloads of the moonshot, moon command module, the lunar module, and the lunar vehicle. The third stage, you probably wonder where, but that is actually sitting in the Earth orbit. Right now, a lot of those are excess, and interesting enough, all of the others are sitting in the ocean, except Linux, one of the guys from Amazon, the head of Amazon, recovered some of the engines out of the ocean last year. If you saw those, that's a video there. So anyway, the next chart. This is where we started. Back here was where a lot of us as propulsion engineers worked in 4610. These are the more built engines, 42, 101, 2, and 3, and then 4200 is further back here. Actually, there is, if you want to know about the Germans, a good friend, Kenny Mitchell, has written a book on cradles of space exploration, which is an outstanding book. And if you want to buy it out here, that's a good treat. Ed Buckby also wrote a book about the greatest space generation. So that sort of covers all of us from our standpoint as far as propulsion engineers are concerned. All right.
Hi, I'm Clyde Nevins. I was born in Montana. My father became an Indian agent, worked for the United States Indian Service, and I grew up mostly on Indian reservations around in the West, 3 different reservations. So it's kind of a mystery I ever got into the space business, but I did. Ended up going to Oklahoma, Enid High School. I was one class after Owen Garriott's class in Enid High School. He graduated in 1948. I graduated in 1949. And then I went to Oklahoma State, got my bachelor's, went to Fort Worth, worked for General Dynamics, working on the Supersonic B-58. Went to night school, got my master's degree there. And then after 7 years, the space program was heating up, and I was looking for a new challenge, so I came to Huntsville to work on the space program. Let me have the next chart. I think 1961 was to me, it was one of the key years in the history of the space program. I know it's not the day we landed on the moon, but it was pretty much the day when the year when how we're going to get to the moon was established. In 1961, as Mickey's already told you, is when President Kennedy made his challenge to NASA. It was also when the Russians sent up the first man to orbit the Earth, and then later on, they sent up another cosmonaut who orbited 17 times. Meanwhile, we were kind of stuck with 2 suborbital flights. We had Alan Shepard and Gus Grissom went up that year. However, America had the first humanoid in space in January of 1960 when we sent up Ham, a 135-pound chimpanzee, in a Mercury Redstone, and it recovered successfully. So it could have been a 135-pound astronaut, but it wasn't. It was a chimpanzee. In 1961, Marshall had just been a part of NASA for 6 months, having transferred from ABMA. There was no Kennedy Space Center. There was no Johnson Space Center. There was a space task group out of Langley who was kind of calling the shots on on the ways to get to the moon. While the space race was heating up, the political climate was also getting hotter. 1961 was also the year when the failed Bay of Pigs invasion. Some of you may remember that. And it was also the year in August when the Russians built the Berlin Wall. So things were getting hot. Anyway, next chart. When I joined NASA in late night, actually I did up my paperwork in December of 1960, and I started the first working day in 1961. Back in 61, many of the buildings that Ron has showed you out at Marshall didn't exist. There probably weren't even any plans for them at that time. A lot of us in the Propulsion Vehicle Engineering Laboratory were here in what we called the Hick Building, Huntsville Industrial Center building. It was the home of Brown Engineering, the founding home of Brown Engineering, and in here were also the launch operations people, because there was no Kennedy Space Center. And this building, what used to be the Lincoln Cotton Mill, it was bought by some enterprising businessmen in Huntsville and turned into office space and then leased to Brown Engineering and to NASA. Next chart. This is what it looked like inside. As you can see, no computer screens, no CAD. This is the way we worked back in then. Drafting boards, drafting machines. And there were several groups in here. Also, at that time, we had Brown Engineering, Chrysler Engineering, and Hayes Engineering contractors working side by side with the NASA engineers. Later on, GAO or someone said, you can't do that anymore, you got to separate out. You can't have contractors working right with NASA people. Also, one of the back in those days, security was a big deal. You had to have a security clearance to work on the space program, and we had clerks that did nothing but keep up with the classified documents. I guess we were afraid the Russians were going to steal our secrets. I'm not sure why all that was going on. Anyway, my group worked right in this area. We called a advanced structural development branch. We were charged with coming up with the structural configuration for the first stage of the Saturn V vehicle, called the S1c stage. I worked for Sepp Blumrich, who was a German, and he worked for a German, and he worked for a German. All our chain of command were Germans. Sepp was not one of the von Braun team, but had come over actually only about a year and a half before. That's one thing, it's not widely known, but there's a good number of Germans came over after the von Braun team and worked in the space program. Next chart. This was our computer back in those days. The slide, and it's a pretty amazing device, and it was used for, I don't know, decades to design some very complicated things. In fact, as I mentioned, I worked on the B-58 supersonic bomber. It was designed with slide rules. It could do a lot of things. It could divide and multiply, raise to a power, take roots. Two things it couldn't do: it couldn't add and it couldn't subtract, and it couldn't tell you what the decimal point was. So there's still room for error. Next chart. The S1c program was unique in the Saturn V series because it was Dr. von Braun's policy that he wanted the NASA engineers to have hands-on experience. He wanted them to work on the actual design hardware and not just monitor what the contractor was doing. So we did the preliminary design, initial design on the S1c in-house, and then Boeing came along and started working side by side and later on in 1961. The big problem with the S1c program was the size, and I'll talk a little bit more about that. It was by far the largest thing ever thought about putting into space. And a lot of those manufacturing problems were designed concurrently with master and Boeing engineers. Also, not widely known, is the first 5 S1c stages, 3 test and 2 flight, were built right here, or assembled right here in Marshall Space Flight Center. Next chart. This shows you, when I started in January, we were working on what we called the C3 configuration of the Saturn V. It was 320 inches in diameter, and it only had 2 F1 engines. So we were working away on that, and then they said, no, it's going to get bigger. And by June, it had already grown to 360 inches in diameter and had 4 F1 engines. And by the end of the year, in December, the final configuration, it was 396 inches in diameter and had 5 F1 engines. Next chart. The design challenges on something that large, first of all, as Mickey had said, this was a man-rated vehicle, and it's very stringent. Particularly, the wheels were the big problem. You can't have any flaws in the wheels, and its trajectory have to be repaired. Also, you have got something this tall and this heavy. You've got to anchor it to the launch pad, and if there's winds blowing, that adds bending moment. So that increases the loads. Then you have 5 places where you've got a 1.5 million pounds of thrust coming in, and you've got to distribute that load so it doesn't overload the tank structure. And to me, one of the problems I would see that I would hate to tackle was routing the propellant lines that have to go through the tank. The propellant lines from the LOX tank, which is the upper tank, actually have to pierce the lower tank. So I guess to be quite a design problem. Next one. On the left, you see the Saturn 1B. This was Dr. von Braun's team had started the design, actually completed the design of the S1B while they were still part of ABMA. In 1961, this was just getting ready for its first long-duration firing. And you see on the right then the Saturn V, and you see the comparison, how much larger it is. In fact, give you a comparison. If you take the Saturn 138 feet tall, next time you're driving down Clinton Avenue and you go by the Russell Erskine Hotel, that's almost exactly the height of the Russell Erskine Hotel. So you can look up and say that's how high the first stage is on the Saturn V. If you take a cut through there, the one on the left is, if you take a section through the Saturn 1B, you can see what it looked like. The blue are the oxygen tanks. The red is the fuel tanks. The red tanks are 70 inches in diameter. So to give you a comparison with, that's about a 5'10" man could stand up in that small red tank, and you see how much larger the S1c tank is. Next chart. One of the trade studies we were charged with, we were looking at what we called a multi-cell tank. It was an option that would maybe, some people thought it might be easier to manufacture, the welds might be easier, and the parts not quite so difficult to form. And so we looked at We looked at the tank on the left. Also, there was a hole down the middle. We thought maybe we could run some of the propellant lines through that hole instead of running them through the tank. So we spent a lot of time looking at that, and it turned out that what we call a conventional tank was chosen. Next chart. We actually ended up doing two different designs, and they built two scale models. These are about, I think, 3 or 4 feet high. I can't remember exactly, to see what they would look like. Next chart. The final design modification made on this S1c was to add an engine to the center of the cross. Somebody asked about Pogo a while ago. If you look at those cross beams and that engine in the middle is and those beams was considered to be one of the causes of Pogo. What happens is you have Pogo, what we call combustion instability, where the engine propulsion flutters. It isn't a constant thrust. It has a little bit of variation in it. And that flutter is about 5 cycles per second, 5 hertz. Also turns out that the natural frequency of those cross beams is about 5 hertz. So when those get in sync, then it just it's called a pogo effect, because it's like jumping on a pogo stick. The more you jump on it, the higher it goes. Anyway, that was the first 4 engines were at the ends of those 2 cross beams, and it was a fairly simple modification that was added late to add that 5th engine. Last chart, please. So by the end of 1961, we had all 3 stages of the Saturn V were defined and proceeding to detailed design. The first stage was contracted to Boeing on December 15th. The S2 stage contracted to North American on September 11th. S4B stage to Douglas Aircraft on December 21st. Now the S4, at that time, that contract was only for changing the propulsion to one J2 engine. In May of 1962, they came back and made a major change to that stage, and it went from 220 inches in diameter to 260 inches in diameter. Anyway, the Saturn V would put about 280,000 pounds in Earth orbit and 95,000 pounds to the moon. One difficulty, though, we didn't know how we were going to do that. Whether it was going to be Earth orbit rendezvous or lunar orbit rendezvous. They were still debating that at the higher levels. They did know that the Earth orbit rendezvous would require at least 2 Saturn vehicle launches and to assemble a moon vehicle in orbit, whereas the lunar orbit rendezvous would require only 1 Saturn V launch. So, as Mickey said, Dr. von Braun jumped on board of the lunar orbit rendezvous, and that's the way we ended up. Thank you. Yeah.
You referred earlier about lack of computers back in 61, 62 time frame.
No, he is. I'm next, but he's got a question for you.
Testing.
You referred back earlier to the lack of computers back in the 1961, 62
Oh, we did have a computer. There was a computer over in the comp lab. It filled up a big room, big air-conditioned room, and it did the important stuff like orbital mechanics and the payroll. I think everything else was...
Okay, well, what I'm leading up to, later on, when they come up with all these fancy finite element computer programs to do detailed structural analysis, do you feel like that in that time frame that we may have over-designed some of the structures like on the S1c and so forth just because of lack of knowledge and the analytical capability?
I'm sure that that's certainly possible, although being a designer, I believe, a computer can optimize a bad design and still not be a good design, whereas a good designer can come up with a structural arrangement that will minimize the weight, and I think then the differences would be fairly minor. Oh, it did? It wasn't, not in 1961 though, was it?
No, not in 61.
Yeah.
In 63, we got an analog computer to
Oh,
do
yeah,
some of the
eventually we did, yeah. When we finally got to the space shuttle, we all had little computers.
Let me have that.
By the way, I've still got my slide rule, and I did use it in the early years. I know people did use computers, but you did not walk in the computer lab and sit down at something and work it out. You had a box of cards that you took. So no, anyway, as I said, I'm not, I didn't work in the fabrication lab, but and somebody told me I didn't tell a little bit of my resume. I was born in Oklahoma in my grandfather's farmhouse. Started a grade school in a little town called Favens, Texas, just east of El Paso. 13 different schools later, I was kicked out of a bunch of them. I graduated from high school in 1952, went to Oklahoma A&M, same place that Clyde went, got my bachelor's degree in mechanical engineering. Started work at Marshall in September 1960. I spent also a couple of years working for my Uncle Sam out at White Sands. Okay, next chart, please. Okay, we'll hit, you can read that. Let's go to the next chart. As Clyde said, in 61, Boeing started working with Marshall. They had almost 500 people on site at Marshall and 600 down at the Hick building. And he told you what we built here. The reason, by the way, that we built these first two flight stages at Marshall, Boeing at Michoud had to build a tall building so they could assemble the Saturn S1c in a vertical position. And I'll tell you why in just a second. Okay, next chart. They started the manufacture of the S1c stage at Marshall in '63, but the parts were being built earlier than that, and 90% of the parts were built by Boeing at the Wichita plant and shipped to Marshall. The bulkhead was made up of 8 large gores that are shaped like a pie, and the tooling was at Boeing, Wichita. The plates that made the walls of the S1c stage tanks weighed 5 tons each before they started milling them down to where it got down to 1 ton. There's 2.3 inches, or the stiffeners sizes. The walls themselves, they say, is about 1/4 of an inch, a little bit bigger maybe. As Clyde mentioned, the welding was a major problem, but they did find that the best conditions were if you kept the temperature below 77 degrees and the humidity below 50%. Okay, next chart. Sorry about the quality of these charts, but this is one of the gores for the bulkheads, and they were made, as I said, at Wichita. This is one of the plates that started out at 5 tons and was milled down and wrapped around here, so it took the shape that you could use to make the cylinders. Okay, next chart. This is what one of the bulkheads looked like, and of course the welding they had to do down through here. Next chart. This, and by the way, all the welding was machine welding. It wasn't a man doing it. As you can see here, here's a man following the machines. It's welded to the dome to what they called a wire ring. Next chart. These are, I believe that's the upper lock, fuel tank, lower, and this is one of the rings, and you can see it's got one already down here. This is the LOX tank, the support structure. Next chart. Here's the upper structure between the two tanks being attached. Here's the finished fuel tank. And here's where they're mating the two tanks. And as Clyde mentioned, those pipes going down through the stages show there. Now, as I said, here at Marshall, the building was not tall enough to have assembled vertically, so they did it horizontally. But, go ahead, next chart. This is the S1c T, the first stage that's going to go to the static structure. The engines attach here, 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 and in the middle. The engines weigh a little over 9 tons. And if you can imagine trying to get some ground support equipment that hold those engines steady and trying to attach them in the horizontal position is almost impossible. So they actually attach them, as you've seen a little chart here, just a second out the static test stand. I think you gave up. The tires, if you notice there, in the other one, the return, they're turned one direction and they'll turn 90 degrees. So go. Okay, next chart. This is on its way to the static test stand. And by the way, they had to build roads here at Marshall in order to accommodate this size of a vehicle. And also they built a road down to the dock down on the Tennessee River. And that is not my chart. Well, okay, we'll just skip the others. That's okay, Jack, don't worry about it. The next couple of charts is showing them attaching the engines while it's in the vertical position as a static test stand. And as I said, the reason for the things, well, we didn't have a building, number one, to do it. Number two, at 9 tons, it's pretty hard to hold that thing like you need to. Okay? Let's do a little testing here, Ron Teeple. This is where things got really interesting.
If I quit talking, it's because I ran out of breath and I got to breathe. I got one. Yeah. Okay, I'm Ron Teeple. I was born in Evansville, Indiana, in my father's home in 1940. I attended parochial schools my whole life, 8 years in the Catholic grade school, 4 years in a Catholic high school, and 5 years at a Methodist university. I went to college on an athletic scholarship. The advantages of that were you got meal tickets, you got free books, and since I was majoring in engineering, I got to keep my books because nobody else was majoring in engineering on the athletic programs. So in college, I had a classmate and a fraternity brother who co-opted at Marshall Space Flight Center. I'd never heard of it, but I do remember when I was a junior in high school, I was going into history class one day, and the teacher announced that the Russians had put up Sputnik 1. So that was the beginning of my knowledge of the space program. But the guy that was my fraternity brother, J.C. Agnew, he lived in Evansville also, and he co-opted down here, and he said, "You'd like that down there, Teeple." So I came down here, went to the Mexican restaurant on the Parkway and Governor's Drive, El Camino, La Palacio, whatever. That was the personnel office for Marshall Space Flight Center. And it was. That's where they had the records, and I went in there, and they had my name because I'd sent them something. And then in each motel room, that was a former motel, each motel room had 2 recruiters in it. They were recruiting people to work for NASA. So they called out at the center and said I was coming out, and I was interviewed by Joe Lundy and Harry Johnstone, Jan Muck, one of those data dogs that Ron talked about. He was in that same group. So I decided to go to work there. Well, on my way down here, I came 431. That takes you through Lewisburg, Fayetteville, Pell City, or whatever it is up there on the hill, Park City. And then when I got to Alabama state line, there was a big sign. It was like a 4x8 sheet of plywood. Had a 3x6 picture of George C. Wallace on it. And it said, George C. Wallace and 275,000 Baptists welcome you to the state of Alabama. So I figured they must have paid for the sign. So that's about all I got to say about that. But when I did get here, I know that I've seen 6 malls built, 5 tore down, 1 remodeled, 1 rebuilt. We started out with strip malls, and now we're back to strip malls. And Sparkman Drive was a dirt road, and they were breaking ground for Brown Engineering's building that's on Sparkman Drive now. Also, there was a big ditch right down the middle of Drake Avenue, and I'm sure the older people remember that. Before I go on, I noticed a few guys here. George Horst back there is one of the old Test Lab Apollo guys. Tim Jernigan is one of the old Test Lab Apollo guys. Bob Pride is one of the old Test Lab Apollo guys. I saw John Thomas in here a while ago, and he was pre-Apollo Test Lab guy. Okay, next chart. Oh, I was going to talk this while I was... Anyway, no, we lived the dream. Go back that one chart. Those are Apollo testing at Marshall. Those are all test sites, system test sites, where we tested for Apollo. Next chart. We also tested at other test sites. We tested at Santa Susana, both J2s and F1s, Edwards Air Force Base, F1s, Sacramento, S4Bs and S4s, and Mississippi Test, S2s, and S1Cs. Next. Why was the Apollo program a success? Largely because of the Saturn program, in my opinion. Why was the Saturn program a success? Largely because Marshall Space Flight Center had expertise in the following space propulsion: management, design, manufacturing, and testing. And they were selected to be the center to develop the booster. Next page. I'm going to talk a lot about testing now. We did a lot of testing at Marshall. Dynamics, testing, the dynamics laboratory, running all kinds of tests: vibrations, shock, acoustic, modal, slosh. Structures, ran pressure tests on tanks, structural loading, bending, all kinds of hot and cold tests. Quality ran many, many tests. They done all the cycling and flow, component acceptance tests, environmental, and then test lab did several kinds of testing. Some was hazardous and some was non-hazardous. And kind of the way we did that, all hazardous tests were done behind the gate. There used to be a guard gate coming into the test lab. All non-hazardous tests were done outside the gate. An example of non-hazardous is valve checkouts, bench checkouts, swing arms. We did all the swing arm testing outside the gate. Inside the gate, we did hazardous component and systems tests. So testing contributed greatly to the success of the Saturn V. Next chart. Okay, this is a post-Apollo buildup. Look at there. When I got here, that was a hole in the ground, and that was a hole in the ground. None of the rest of that west area was here. Nothing from here towards us was there. There was a lot of construction going on. There were cars everywhere. There were welding machines, trucks. They were building tanks. They were building everything. They were pouring concrete. Those concrete pillars are 14 inches thick. On those walls are 40 inches thick some places. And that goes down to bedrock. So from 1963 to 1965, all of that area there was built. That's a 6 million gallon storage of water, 13 diesel train engines to pump it, 285,000 gallons going to that deflector for testing the S1c. That's the F1 test stand there. We used to deliver propellants by rail, later by truck, but initially we brought in rail cars full of propellants. That was the control center and the data center. Also going on at that time was the construction of Mississippi Test Facility and the launch facilities at the Cape. Also at Marshall, we were building the Saturn V Dynamic, the F1 turbopump stand, the west side of the tower, and the S4B stand. So all that construction was going on between 64, 62 to 65. Next chart. Okay, this is a static test hour east. That's where we tested the Saturn I. There were 31 tests on the S1c T, and those were in 60 to 62. The S1 flight stages, there were 24 tests on 10 different vehicles from 61 to 64. And on the S1B flight stages, there were 32 tests on 12 different vehicles from 65 to 68. That's a lot of testing, a lot of fuel, and a lot of hydrogen, LOX. During these tests, they were testing the flight stage one day, and the astronauts were here. So two of the technicians, Paul Kennedy, who was the supervisor of the techs, Ronald Chittum, who was one of the foremen, walked around that platform up there while that was firing to demonstrate to the astronauts how safe it was. Okay, this is the F1 stand, which we call the Static Test Hour West. We ran 75 tests on 16 different engines from 1963 to 66. The 75th test was a blow-up. We blew the engine up. But the reason we blew the engine, well, let me tell you about the techs. We had great technicians. and test lab. Most of them came from the Air Force flight line, working on jet engines. So I had Horse, Fat Boy, Yogi, and that was their nicknames. Horse was Tom Linan, Yogi was Charlie Yeager, Fat Boy was Bill Stinnett, and Tim Jernigan didn't have a nickname. So, and those who didn't work on the flight line in the military on jet engines came from the farm or from construction. You know, they were welders. They were people who were good with their hands and learned how to work. And we worked. When I came here, I think I made $2.76 an hour, which works out like $5,800 a year, something like that. We doubled our salary every year until we landed on the moon. So that's how much we worked. We only got time and a half for overtime, too. So we put in a lot of hours. But this is the west side, the Static Test Tower West. We ran 75 tests on 16 engines. And like I said, the last test, we blew it up. And what happened there was the Cape was playing with the idea of emergency shutdown for the stage on the pad would be the pre-valves. We told them you can't close the pre-valves or you'll blow the engine. They didn't really believe that, so we loaded a little LOX and a little fuel and closed the pre-valves, and that blew the engine up. The engine was we put it together out of spare parts down in the prep shop, but we still blew it up. So that was one of the 16. Next chart. And this is the H1 F1 turbopump stand. That was the H1 stand, F1 turbopump stand. During the activation of the Static Test Tower West that I just showed, we were timing the pre-valve and we were flowing water without an engine, and we signaled the pre-valve to close, and it slammed shut in 10 milliseconds. So, and we were flowing 25,000 gallons a minute. So we had a large water hammer and tore up the valve supports and everything. So we had to fix that problem because nobody knew when we'd have to use it if we blew an engine off the bottom. So we took it over to the F1 turbopump stand, which had the flow capability of 25,000 gallons of LOX and 17,000 gallons of fuel, which the F1 burnt. And we solved that problem with that pre-valve over there. We didn't burn. The burning you see here is an F1 GG driving the pump on that stand, and that GG is about 35K. But we didn't run the GG, we just flowed back to the catch tanks. But we fixed it by putting a snubber on the exhaust side of that actuator. Next chart. This is the power plant test stand, which John Thomas ran back in the old days somewhere. And between S3D engines and H1 engines, it ran 528 tests on that stand. Next chart. This is the J2 engine S4B static test stand. Now, it has a battleship tankage. On all of our engine system stands at Marshall, we simulated from the tank to the fire out the exhaust, the flight stage. So we always had flight ducts, supply ducts, the LOX ducts, the fuel ducts, the pre-valves. Everything from a battleship tank out was flight weight, which is unusual. Normally, on all of our development stands, we had battleship lines. So, and they're designed 3 and 4 to 1. The flight's designed like 1.25 to 1. So, and on that stand, they ran 154 117 J2 engine tests. And we had another battleship stand down at Old Plants Area 1 across from the firehouse where they ran 154 RL-10 tests. Next chart. F1 engine test stand in the west area. We ran 107 tests there on 13 engines from 765 to 769. So you see, everything's ending about the time we're going to the moon. Next chart. This is the installation of S1c T. When we put it in that day, I was standing beside Dr. von Braun and Walt Disney. And it was built and brought out there, and we hooked it up, start rotating it, and you start hearing ding, ding, dong, ding. And Walt Disney asked Dr. von Braun, he said, "What is that noise?" He said, "Well, that's stress relief. We built it in the horizontal, and we're rotating it." But it was actually nuts and bolts and washers. So we installed it. It had no engines on it. We flushed it with LN2. We got a lot of junk out of grindings and things out of the 2 tanks, but we mounted the engines. We fired it the first day with a, we'll go to the next one. Next slide. That's a 5-engine firing there. But the first time we fired T-Bird, we did it with 1 engine. And the 1 engine in the middle, and that engine, later we found out that when it rebounded, it broke 4 of the 8 bolts holding the thrust block to the stage. And we couldn't figure out what was going on. And we finally determined that they were high-strength bolts. They should have been torqued to 600 inch-pounds, and they were torqued to 600 foot-pounds. So they had so much load on them, they were like a piece of glass when we hit them. So that's one thing we found. We found a lot of things doing all this testing, and that's why the thing worked. But anyway, on the first test, Robert Pride, still sitting back there, was standing. We both had cut buttons, and I was watching the engines. He was the stand engineer. He was the one in charge of all the LOX engineers and the fuel engineers and the hydraulic engineers and all those people. And it started, and we used to have a ring purge around the engine that would blow out, and the hypergol would come down and just look like the engine was running. But Harry Johnstone was counting it down, and he said, since we only got a little bit of LOX and a little bit of fuel, and we don't have any experience on this GN2 pressurization system, and we're pressurizing both tanks with GN2, he said, I'm not going to turn that ring purge on, so if you need it, you call for it. Well, that's a lot of good. But anyway, the bottom of the S1c stage, 33 foot in diameter, had 2 inches of thick asbestos on the bottom for a heat shield, because everything balloons out as you get the atmosphere. Well, when that hypergol burst, and it come rolling out of there, and when it got up to that blue heat shrink that was on that asbestos, it just turned white hot, and I cut it. I thought it exploded. And Bob Pride said, why'd you cut that? I said, I didn't cut it. He said, yes, you did. I heard your cut button. And so about that time, Joe Lundy and Heinberg and Von Braun and James Webb. They were all in the control room. And my boss was Joe Lundy, and he came down there, who in the hell cut that engine? And I said, I did, but we'll be ready to go in a while. So I took off and got Fat Boy and all the techs, and we went out, rolled the deck in, drained the engine out of RP1, flushed it with trike, put new hypergol in, put new squibs in the GG, rolled the deck back out, came back up to the test stand, and we couldn't find Tom Shaner. He was down playing with his hydraulic pump. So we finally got him back up to the control room, and we fired again. And that time it ran 30 milliseconds longer than it did when I cut it. And I took a lot of flack for cutting it, I'll tell you. But what happened then was, if we looked at the data, we probably would have known it. But the one fuel valve reached open before the other one left closed, and that was an automatic cut, because you would go locks rich if a fuel valve fails to open, you would end up locks rich and burn the engine up. So it cut automatically. So then we went to the officers club for a party, because they have these corporate tables after big events. And Von Braun came and got me, took me around the corporate tables, and introduced me as the guy with the golden thumb, because Goldfinger was the movie at the time. That was what was going on there. So we fired that stand 22 times. We fired T-Bird and the first 3 flight vehicles there. The third one was built in Michoud, but it was fired here at Marshall. They weren't ready to fire yet, from 66 to 67. First time that fired, Birmingham measured, they thought they were having an earthquake, and we broke the windows out of Wolverine tube in Decatur. So that was caused by a temperature inversion, where the sound goes up, hits a temperature inversion, and bounces down and concentrates. So we put in a big horn, put microphones 1, 3, 5 miles out, and we'd blow the horn. They'd tell us whether we could fire or not, when the temperature inversion had gone away. And normally that happens when the lake gets smooth. There are no more temperature inversions when your lake can smooths out at night. So we'd get ready to fire about lunch and then end up firing late in the afternoon. So next chart. All right, we had 192 Marshall managed static firings at various sites. And Jim Pearson managed all those S4B tests at Sacramento, those 80 S2 tests and 15 S1c tests were at Mississippi Test Facility, which is now Stennis Space Center. Next, and that's why we lived the dream. Now, at this time, when we landed on the moon, we were all looking for a job just about, because, we got done early before they landed on the moon, and we laid off a bunch of people, and it was first in, last out, that kind of stuff. So it was tough, and we went to work on coal gasification and different things, and then along came shuttle. And in the meantime, we worked Apollo Soyuz, and we finally got to go on the shuttle, and that continued the dream. That's it. Thank you.
Okay.
I've got a question. Moving on. Pardon?
Okay,
Testing, I think, versus all-up testing.
okay.
Do you have any comments on all-up testing?
That's the way to go if you're safe. If you think you can do it without blowing the whole thing up. All up is the way to go. Component testing is, you need to do it. But I would never all up test the first time. You know, it's got to go through its, yeah. And another thing I was going to tell you, oh, excuse me. Somebody asked about pogo a couple times. Now, pogo is induced by the engine basically pulsing because of the fuel feed system. The LOX and fuel feed system is oscillating back and forth. So that oscillation feeds all the way through the engine, and so the engine thrust oscillates a little bit. And why that's so dangerous is if it gets bad enough, of course it'll destroy the vehicle. But in our case, we had 3 astronauts up there, and their gut frequency was the same frequency as the pogo. So we could not let our vehicle pogo.
Okay, you need to know that the one that asked that question, you tell who you are.
It doesn't matter.
Yes, it does. This is Karl Heinberg's son, Klaus
Well, good.
Heinberg.
We used to drink at your father's house. Well, Sid, like I said, it got interesting. And since you're Dr. Heinberg's son, you say? Karl Heinberg's son?
Karl Heinberg has passed away.
Yes, I know, but I mean, you're his son. Well, I've heard that he said he would not allow anybody in the test area unless they were a test engineer. If you wanted something tested, you gave it to this guy, and he'd take care of it, but you didn't go in. So he was tough, I understand. We meet quality at the gate and get the logbooks. They were not allowed.
Well, folks, I'm Brooks Moore. I'm a country boy from Hamburg, Alabama, and I'm sure there's probably not more than one person here other than myself that knows where Hamburg is. 2, 3, 4, thanks. Hey, I never knew that you'd heard of Hamburg, but I see these familiar faces now. But anyhow, it's sort of halfway down the state, north-south, and sort of halfway east-west, so it's right about in the middle of the state. But anyhow, I was born and raised there. I went to schools, went to Hamburg Junior High School and Perry County High, and I often say that all I needed to know I learned it in one of those 2 places. All I needed to know was to help send men to the moon. That's sort of a little bit of a exaggeration, but anyhow, Hamburg, after I finished Hamburg Junior High and Perry County High, we're right in the middle of World War II, and so I had the pleasure of serving 2 years on active duty with the Navy. And when I got out of the Navy at the end of the war, I went to Auburn University, which had been my plans all along, to enter engineering school, and they got a degree in electrical engineering. I also decided I would continue my ties with the Navy. We had a Naval ROTC program at Auburn, so I took Naval ROTC, and at the same time I graduated, I got a commission in the Navy and served for 10 years on the reserve Navy. After Auburn, I went to Georgia Tech, got a master's degree in electrical engineering, and kept up my ties with the Navy. I got an offer from the mine torpedo countermeasure station in Panama City, Florida, and I took that job. And was working there when I heard a little bit about the rocket program in Huntsville, and when I was home, let's see, I guess it was about 1951, I came up for interview and accepted a job. So I've been here for 67 years. And I've maintained my continued interest in the space program and in the rocketry. And I'm still involved to some extent, not making a lot of contributions, but keeping up what's going on. But it's been a long afternoon for all of you, and if you leave during my presentations, I will not be offended. But what my topic is, instrument units for the Saturn family of launch vehicles. We refer to it as family because in addition to the Saturn V, as several of the speakers had mentioned, we had two earlier systems that we used for testing leading up to the Saturn V, and that was the Saturn I and the Saturn 1B. And both of these were intended to be test programs that supported the ultimate the design of the Saturn V. But on the instrument unit situation, we needed to have a separate structure on which to mount our instruments, our electronic systems. This was a luxury we didn't have at ABMA and the Guided Missile Development Division. The propulsion and structures people built the rocket, and then they reminded us they need to put a guidance and control system in. So we would hang our electronic boxes wherever we could find space. We really didn't have the equivalent of an instrument unit. But anyhow, we realized that the complexity of the Saturn V system was going to be such that we needed to have essentially a structure that that we could actually call our own as far as the mounting of an instrument. So we evolved it through the Saturn I program. There were 10 launches of the Saturn I, and I want to, first slide, please. This is what I think Clyde or someone already showed a cross-section of this. This is what the launch vehicle looked like, the first stage of the Saturn I. It was made up of a Jupiter tank with 8 redstones around it. Those were our rockets we had developed for ABMA. And, but right in the front, and I don't know if I can use the pointer or not well enough to point, but you see 4 canisters there at the top of 4 circular. And we use that as a let's see, is it going to point? Okay. Well, anyhow, this percentage right in here, these are, I'm not going to be able to, but you can see the 4 canisters. That was the first step. We put our electronic equipment in the canisters, and that turned out to be not a very satisfactory solution because of access was very, very poor to get into doing things to electronic. But we did use that for the first 4 flights, which were just tests of the first stage. Beginning with the fifth flight, let's have the next slide. We actually built a structure that's a ring sort of thing. It's really an odd shape, but it was the first attempt to come up with an arrangement where we could mount our electronic equipment all in one structure. That was worked, as I say, reasonably well. I would like to point out that the first of this we put up a stage on the SA-5, and that was our first test of this instrument unit. But the significance of SA-5 also is that with the upper stage of a 90,000-pound thrust, and we had 1.5 million pounds of thrust on the launch vehicle, we surpassed the Russians in their largest launch vehicle at that time. that's a major milestone. It's a side issue, but I thought I would just mention it. It took us, I guess, 3 years from the time we started the program to catch up. You know, Kennedy's reason for the whole program was to prove we were technologically superior to the Russians. And actually, this is our first step, but we actually surpassed them with our rocket, SA-5. So we had 3 of these IUs all built in-house, instrument units, but we realized that this was not an ideal solution. First thing, it was way too heavy with all that superstructure in the middle. Next slide, please, Jack. So the light came on, the bulb light came on in our heads. Hey, why not just get rid of all that central superstructure and hang the boxes on the inside of the ring, which was going to be the structure that So this was our first step of really getting close to what we ultimately needed in the way of a separate structure. And so we ended up the Saturn I program with that instrument unit. By the way, all the instrument units for the S1 program were built in-house at Marshall. And of course, we designed in-house at Marshall almost all of the electronic equipment that went into that. Let's go to the next slide. This was the ultimate. We decided that ring shape worked very well, and it gave complete accessibility. You can see that there's no problem getting to any electronic equipment in this. We got these plates around the inside of the IU that we have mounted the electronics on. So this was the first flight of the 1B. We used this instrument unit. It had to be significantly larger than the earlier version I showed, because we had with the start of the Saturn 1B program, we had taken the S4B stage, which was going to be the 3rd stage of the Saturn V, and the Saturn 1B was a test vehicle where we already were testing some of the components that were going to go on Saturn V, including the instrument unit. So this was a step where we did have to go up to a larger instrument unit of 22 feet, and that was to match the upper stage, the 3rd stage, which we were testing on the Saturn 1B. But you might see some of the features there. By the way, one significant thing we had to do different from the Saturn I, the Saturn I was all lob shots. We did not go into Earth orbit with Saturn I. Saturn 1B was our first vehicle where we had the significant power enough of our first with 2 stages to put a crew in Earth orbit. So that means we have to have some means of cooling our electronic equipment. And what we chose to do was to have what we call cold plates, those little plates that are on the inside there. I guess I'm not going to. But anyhow, you can see that there are about 25 plates around the inside there. The plate's about 2.5 feet by 2.5 feet. And we flowed methanol through those. It was essentially a refrigeration system, and then we mounted the electronic items on those plates. Some of the larger items took up the full plate side, but you can see boxes over on this right side that there's several boxes on one of the plates. As far as other features, we had an access door on the side down here. There we go. There, right there, and that was to so we could go in and do troubleshoot and do work on the IU after it was stacked at the Cape. we had, it sat on top of the S4B stage, and on top of that was the spacecraft, the 100,000 pounds that we sent to the moon. So if you need to get into this to do any troubleshooting, you can physically get in that access door. And the other features, you see a couple antennas there. We had actually 5 RF system links, so we had 5 antennas. But anyhow, this worked out to be very satisfactory in every regard, I would say. So let's go to the next slide. This is some of the subsystems that we had in the instrument unit. Of course, we needed power. It's all electrical system. We had silver zinc batteries, 28 volt, and we had to do some conversion to satisfy the needs of some of the black boxes. We call them black boxes, and not a single one of them black, but that's terminology that we use in the electronic industry. The black boxes, electronic boxes. But anyhow, we ended up using several different techniques of voltages actually to supply all of our black boxes. And you've seen the complex distribution system, that array of wires that run around the top of the vehicle. One of the key functions of the is the guidance and control of the vehicle, and that means control is stabilizing it, keeping it flying straight. It's control to pitch, yaw, and roll, essentially. So we keep the vehicle flying stably, otherwise it would tumble. Guidance is pretty much knowing where you are and where you want to go and guiding the vehicle to the target. Another key function of the launch vehicle, digital computer we call it. By the way, the 3 major components of the guidance control system was a digital computer, which the first time we were the first people to fly a digital computer on a rocket. And but we had to have it for the sophistication of the guidance requirements for the lunar landing. So, so we had a guidance computer. We had a control computer. The way we controlled the vehicle was by gimbaling the outboard engines on the stages, and we could do pitch, yaw, roll. We apply those forces to keep the vehicle flying in a controlled direction and also to the target. And we had a sensing system that we called a stabilized platform. That's a gyro-stabilized electromechanical device, about 18 inches in diameter. But it gives us we can measure the angles that the vehicle rotates around and make those corrective signals. Also, we have accelerometers on that stabilized platform, and they measure the translation, and we can integrate that twice and know what the position is that the rocket is straight from the trajectory, so we can return it by, here again, gimbaling those engines through the control computer. Another key function was staging the vehicle. As you know, we have 3 stages, and we burned those sequentially. So our system actually controlled all aspects of the propulsion system from the standpoint of starting at the launch site. We give a signal from the instrument unit to unite the engines on the S1c stage. When we expend the propellant, by the way, we're monitoring the propellant also, and that information is fed to the launch vehicle digital computer. But when we are approaching burning out of all of the fuel, we send a signal to the first stage to cut the engines off, and then we send a separation signal of explosive bolts that allow you to separate the S1c, and then we have retro rockets that pulls it away, backs it up, so with no half collision there. And then the next step is to ignite the engines in the S2 stage. And all that's done by our computer in the instrument unit. And of course, we repeat that sequence between the S2 and S4B. Instrumentation, we had to make measurements of all functions, temperatures, vibrations, propellant levels, propellant flow rates, most anything you can think of, we had an instrument to measure it. And there were 200 of those instruments in the instrument unit, and others scattered throughout the vehicle that were fed all back to the launch vehicle digital computer. By the way, that computer was essentially the brain of the rocket, because we had other electronic items that were part of that, but the focal point of all that was the digital computer. We had the communication systems with the ground. We fed all of this measured information to central control, but it also went to the launch vehicle digital computer. We had 5 different communication links to send the data of all the measurements so that we were reading in real time at central control what the conditions were in the vehicle, and also we had that for historical purposes to review afterwards. We had 2 transponders for radar so we could keep track of where the vehicle was. Of course, we had that on board with our stabilized platform and digital computer. We knew where we were at all times, but as a backup, we did have a radar system. We also had a communication where we could communicate with the launch vehicle digital computer when we arrive in Earth orbit. You know, we go into Earth orbit and stay around for a couple of revs, and if there were anything that needed to be updated, we had a link that would allow us to do that. Let's have the next one. By the way, I know we're late, and if you'd all like to leave, please feel free to do so. But anyhow, a major contractor support. Just like in the other stages, we did need support. So the contractors that we dealt with, when we realized that we were going to have a digital computer, we did the wise thing, and that was not try to do it ourselves, although we designed all the other electronic boxes. But that seemed too complex for us to try, so we looked around, found a contractor we felt was very capable, IBM, and so we got them to actually design, with our assistance, the launch vehicle digital computer. I mentioned already the stabilized platform and its function. That was designed totally in-house. We had a team at the core of the German team that had been working on this for some years, and it was all done in-house, and even, we built 2 or 3 or 4 of them, but for the number we needed for both the Saturn 1B and the Saturn V, which was 17, I guess, total, that would be flight items, we needed assistance, so we found Bendix was a good contractor for that. Also, when as far as integration of the vehicle, of the instrument unit, building in the numbers for flight, we needed a contractor. We had good relations with IBM, and so we chose them to do that integration work also. Let's go to the next. Okay, this is what, by the way, let me just comment that going out to industry to get assistance in building the various portions of the vehicle was, we did that with the propulsion systems. Boeing had the first stage. I think someone's already covered the North American second stage and Douglas third stage. We likewise needed that kind of help. And we had selected IBM. Dr. Von Braun was extremely concerned about this box, this system being done in Owego, New York, where the Federal System Division existed. That was a little bit too remote. So he required IBM, if they accepted the contract, to build a facility in Huntsville where we could work with them on an everyday basis, and that's what we did. IBM built a place on Sparkman, which was 2 blocks away. So we spent a lot of time with them, and they spent a lot of time with us. But it turned out to be an excellent team arrangement, and they built in this facility, I think with 27 total. We only needed 17. We needed the 12 for Saturn V. We needed 5 for the previous for the 1Bs, and then we had other functions after the lunar program that used the portions of the Saturn vehicle, and that was Skylab and the Apollo-Soyuz test program. So we needed about that many. Of course, we've got 2 over in the museum over here, one that's suspended along with the other stages, and one that's just standing upright on the side of the wall where you can get a close look at that. But that's our program. We had no success, no failures, all successes. Not only of the lunar program units, but the subsequent those things that we worked on after the lunar program. So we had no failures within the IU. Nothing. We had redundancy in all of the critical systems. That means we had triplicated some of the systems, and we would compare. And if it was a discompare, we would switch to a third system. We used that technique pretty much throughout, and particularly in all the critical programs, critical aspects. But we just even never had to switch to the backup. I mean, and of course, some people say you over-design, and of course, that's encouraging to us. We wanted to over-design. Our mission was to not lose a life on this program, and we made it. We got back all the astronauts, and I would say that may be considered a minor miracle if you know the complexity of the Saturn vehicle, the Saturn V. But we managed to, with great care in every single item, and we tested at all levels, including after we got everything together in the IU, we ran a complete test of every function before that left Huntsville going to the Cape. So this turned out to be an extremely successful program, and we are proud of it. And I want to ask if anybody from Astronautics Lab is here. That's our laboratory. I failed to mention earlier that I was in the control area from the time I came here in 1952, and I headed up the Guidance Control Division when we became a part of NASA, and I served in that capacity for 8 years, and then I became a laboratory director of the Astronautics Lab, which means the space electronics. It's just like equivalent of avionics for aircraft. We call ourselves Astronautics, and but I had a pleasure to serve in that position for about the last 5, 6 years of the lunar program. So that's my story. And is anybody here that worked in the Astronautics Lab? Except Tim. Tim is you and me, it looks like. But I'm glad I'm not the Lone Ranger. At least we got Tim here with me. But we had 600 engineers and technicians in the Astronautics Lab. It was not a small effort. And they were all extremely capable and conscientious. And some people, one of my close friends kid me, by the way, the instrument units also have nicknames like the IU and the ring, And the brain, it is the brain behind the vehicle. Everything was automated. The astronauts did not control anything in flight. But my friends kid me about being the brain behind the brain, and I said, no, Dr. Walter Horseman, one of the regional German team, was the brain behind the brain, and I worked for him. He was my mentor for 17 years, and I worked for him, and he was a very astute guy that I consider he's the brain behind the brain, and I just sort of was fortunate enough to be able to follow him. But thank you for your time. I'm sorry it took so long.
We will have a question and answer, but I want to give you some information really quickly before you get away. Next week, the 20th, we'll meet back in this room. The Marshall Center directors will be here. You'll hear some very interesting stories. We've actually already heard this out at NASA, and there's a lot of humor and a lot of good stories about each of the center directors as they tell what happened on their watch. Simultaneously on that day, not at the same time, but at 6 o'clock. First off, the center directors will be here at 2:30, but 6 o'clock that evening down at the library, Richard Hoover, who is a NASA scientist, will be here down there, and he's going to talk about the Marshall's role in manned rockets, space probes, and instruments for the moon, cosmos exploration, and he's going to talk about why they believe that there is actually water on the moon and how they're going to prove that, and he believes that there in fact might be life in that world. So just pass that on to you. So now we're going to turn it over for questions.
Any questions?
One more on the 27th.
Well, I want to thank all four of these gentlemen for participating in this and helping me do this. I really appreciate it very, very much. By the way, there's also two other people here that I see. Maybe I don't see the third one. This guy right here, Heidi Collier over there, helped me tremendously getting this together. When I needed some help, they did it.
I got one more thing. We had a photo there of the pool, Sonny Mariah, some of the other guys. In the background was Dave Arnett. He's the only Marshall employee. Can everybody hear me? No. You can't hear me? We need it on the tape. What did I just say? Okay. Dave Arnett, whose picture was in a couple of the photos there, he had a very interesting career at the Marshall Center. He is the only Marshall employee at his retirement party for his chief engineer to give him a plaque that says, Dave Arnett did hereby work on this project and this project, thereby proving that you did do some work at Marshall during your many years. Some of us here know Dave Arnett. Speaking of Dave Arnett, he's one of the clumsiest guys I ever played basketball against, and Ron knows, but we have to mention Ron Bledsoe there. He said that he did flunk out of Navy flying school. Now, I get this from other people, mainly Dave Arnett. He's clumsy. I didn't play basketball against you. He's clumsy and uncoordinated. As he's taxiing out to the runway in an airplane, he washed out. He almost ran over 2 trees and 2 other airplanes. Right?
These guys are just engineers. Clyde showed you the little slide rule. Back in the early 60s, though, us engineers would argue with other engineers, tell them they didn't know what they were doing and everything. But there was one group of people that was absolutely, you did not argue with. You treated them as nicely as you could because they did some fantastic work for us, and that was the secretaries that we had out there. Are there any people here that worked as secretaries during the Apollo program? Stand up, please. You deserve a big, big hand because you did a great job. Okay, that concludes our program, and thank you very much for coming, and I hope you enjoyed themselves.
3, 2, 1. 0.